Hey everyone, I'm Dr. Manu, Professor Nirmala College of Pharmacy, Moatupura. Today we are going to discuss a new topic, that is the instrumentation of IR spectroscopy. Last day we discussed about the basic principle of IR spectroscopy, where we see that the IR spectroscopy is mainly used for the identification of functional groups. So we can identify the compounds by comparing the sample spectra with a reference spectra. We can easily identify the compounds. Okay, it's just like a fingerprint. So we can easily identify the compounds. So today's topic is the basic components of IR spectrophotometer. So upon completing this topic, you will be able to describe the construction and the functions of major components of IR spectrophotometer, which include the IR sources, monochromators, interferometers, detectors, and sample holders. And also you will be able to differentiate the dispersive IR and FTIR spectroscopy. We can see the main advantages, limitations, and applications of these techniques. So these are the course outcomes we expected from this topic. Let us see the topic in detail. The first one is the dispersive IR spectrophotometer. A dispersive IR spectrometer works in a simple step-by-step way to measure how the sample absorbs IR radiation. First, the instrument produces a beam of IR radiation using a source like globus source. This beam is then split into two equal parts using a mirror. One beam is passing through the sample while the other is passing through the reference or the blank. After this, these both beams enter a monochromator, which separate the radiation into two individual wavelengths. So after that, we can see that this monochromator will separate the whole wavelength, means all spectra, into individual wavelength by one, and this will be allowed to pass through the detector. The detector will compare the intensity of sample beam with the reference beam. So this will help to determine how much radiation is absorbed by the sample. Then the signal from the detector is recorded, amplified, and which is recorded as a graph of absorbance versus wave number. This graph is called the IR spectrum, which helps to identify different functional groups in the sample. So this is about the dispersive IR spectrophotometer. Next slide, we can see the basic components, the schematic representation of this dispersive spectrophotometer. Here we can see this yellow colored ball like circle. We can see this will be represented as a IR source which will emit the radiation. So the mirrors will help to split the radiation into two. So one portion will be transferred through this reference cell where we kept the blank, and the next one through the sample cell. Here we can place the sample, the analyzing samples we can keep here. Then the radiation will be passing through a monochromator. Monochromator will disperse the radiation into individual wavelength. So after that, it will hit the IR detector. So the intensity of radiation can be identified. From that, we can construct a graph of absorbance versus wave number, or the percentage transmittance versus wave number. That IR spectrum can be constructed with the help of these signals. We can see these components in detail. The first component is the radiation source. Radiation source consisting of different types of radiation sources, including nearest globe, globus source, mercury arc lamp, incandescent wire sources we can use, and tungsten filament. These are the major commonly used radiation sources in case of IR spectroscopy. These radiation sources consisting of inert solid which may be heated electrically so that it will make it glow, and it will produce the IR radiation. This IR radiation will be used as a used for in spectrophotometers. We can see the details of each components in detail. The first one is the Nanest Glober. The Nanest Glober is an IR radiation source commonly used in IR spectrophotometers. It is composed of rare earth oxides, mainly zirconium oxide, yttrium oxide, and thorium oxide, which gives its ability to emit the IR radiation when it is heated. Structurally, it is a small hollow tube, typically made up of around 2 to 5 centimeter long and 1 to 3 millimeter in diameter, which is having a platinum leads which is attached on both ends to allow the passage of electric current. This nanest glober is having an important property of larger negative temperature coefficient, which meaning that its electric resistance decreases as temperature increases. When heated, it emits the IR radiation over a wide wavelength range and provide a stable, steady output for a long duration. So, it makes it useful for the analytical measurements. However, the nanest glober has some disadvantages also. It is fragile, so it can break easily, requiring a careful handling. It also needs an auxiliary heater to initially rise the temperature because it does not conduct electricity well at room temperature. Additionally, there is a risk of overheating, which can reduce the lifespan or damage of the sources if not properly controlled. So these are the main disadvantages, but it will produce a stable radiation with sufficient intensity. That is the main advantage. So nanest glober is one of the commonly used radiation source in IR spectrophotometers. And the next one is the glober source. Glober source is commonly used in IR radiations as a source. It consists of rods of sintered silicon carbide, typically 5 centimeter long and 5 millimeter diameter. One of its key property is that it has a positive temperature coefficient of resistance. In previous cases, we see that the nanest glober is having a negative temperature coefficient, but in case of glober source, it is having a positive temperature of coefficient of temperature, coefficient of resistance, sorry. So which means that the electric resistance increases as the temperature rises. The main advantage of glober source is it is self-starting and when it is electrically heated, so it is begin to conduct and emit the radiation as soon as the current is passing through it, unlike the nanest glober. It is usually enclosed in a water-cooled brass tubes, which helps to maintain a stable temperature and prevent overheating during the operation. When heated at a temperature around 1000 to 1500 degrees Celsius, the glober source emits the IR radiation over a wide wavelength range, making it suitable for the IR spectroscopic applications. However, the main drawback is it will produce a less intense radiation as compared to this nanest glober. That is the main disadvantage of glober source. The next one is the mercury arc lamp. The mercury arc lamp is an commonly used IR radiation source, mainly in case of far IR region. It consists of high pressure mercury vapor, which is enclosed in a quartz jacket tube. These mercury vapors are usually filled in a pressure of 1 atm, atmospheric pressure. We use this quartz because it can withstand high temperature and allow the required radiation to pass through it. So quartz is used as a jacket. When an electric current is passing through the mercury vapor, it becomes excited and forms an internal plasma source. In this plasma state, mercury atoms are energized and they require low energy levels, so they emit this radiation that include the far IR range. This source is known for producing intense stable radiation. making it suitable for IR measurement. Then the other sources include the incandescent wire loops and tungsten filament lamp. The incandescent wire loops, actually it is wound spirals of nichrome or rhodium wire we use. Once the electricity is passing through this wire, it produces the IR radiation, or it emits some IR radiations. The main advantage is that it is not required, it does not require any water cooling because it won't produce that much temperature. That's why no water cooling jacket is required, and the maintenance is very less. And also the main disadvantage is it produces a less intense radiation as compared to other sources. The next one is the tungsten filament lamp. In tungsten filament lamp, here we are going to use the spirals of tungsten wire. Here also, once we pass the electricity, it will produce the IR radiation, but it produces the radiation in the range of near IR. That is the main disadvantage of tungsten filament lamp. In case of IR spectroscopy, mainly we use the mid IR range radiations instead of far IR or near IR. These are also useful in case of other studies, but in majority cases, mid IR only we are focusing. The next major component is the sample holder. Before going for the sample holders, let me conclude once again. The radiation sources commonly used are Nernst Glover, Globus source, mercury arc lamp, incandescent wire lamp, and tungsten filament. These are the radiation sources. We see the details also. One more thing, what are the main requirement of these radiation sources? The radiation sources should be, first of all, it should produce an intense stable radiation. That is the main requirement, because it should produce sufficient intensity. That is the main important thing. And also the lifespan of this radiation source is also that's important. So Nernst Glover and Globus source, these are the major sources which is used in case of IR spectroscopy. So we can move to the next slide, that is sample holder. The next major component is a sample cell. In case of liquid sample, these cells are usually constructed of rock salt, sodium chloride plates, because the rock salt is transparent to IR radiation. The path length we can be adjusted with the help of Teflon spacers, so a uniform path length we can ensure. Then these samples usually filled with a help of hypodermic needles. Okay, in order to transfer the sample, we are usually using these hypodermic needles. And one of the most common issue that we are going to face with this sample is the fogging, which is due to the moisture, because we know that sodium chloride is hygroscopic in nature. That means it absorbs water from air as well as from the sample. So we have to be we should provide proper care, which is essential for the maintenance of the cell. The sample must be moisture free to avoid the damage and the interfaces. That is the most important thing. Then the sample plate should not be touched with fingers. That means handling should be bare-handedly. We cannot handle these cells. And also the contamination with silicone should be avoided, because some residues, it may leave some residues that may interfere with the IR measurement. So silicone should be avoided. These are the important parameters, or what are the things we have to be remembered with the sample holders. Next one is the monochromators. Monochromators is usually used for the selecting a suitable wavelength range or wavelength frequency from a polychromatic radiation, as we know already the things, because in other spectroscopy techniques also we see the use of monochromators. Since the IR sources emit the radiation in many wavelengths, that is polychromatic in nature, the monochromators separate this radiation and allow only a narrow band of frequency to pass at a time for analysis. This is the main function of this monochromator. Then we can see mainly two types of monochromators are used in case of IR spectroscopies. Then the first one is the prism monochromator. which work by passing IR radiation through a prism. A prism, we know that which disperses the radiation to its component wavelength due to the difference in their refractive index. Each wavelength bends at a different amount, and by rotating the prism, different wavelength can be selected. Okay, this already we seen in case of other spectroscopic techniques. And the next one is the grating monochromator. In grating monochromator, we are using the diffraction gratings we are going to use, which has many closely spaced parallel lines. When IR radiation strikes on the gratings, it is diffracted and spread into different wavelengths. By adjusting the angle, a specific wavelength is directed towards the detector. The most important thing is the material used for the monochromator should be transparent for IR. That is the main important thing. So in case of IR spectroscopy, we mainly using the halogenated salts like sodium chloride or potassium bromide, which are commonly used material for the preparation of these monochromators. These materials are chosen because they are transparent for IR and allowing the IR radiation to pass through without significant absorption. However, they are sensitive to moisture, so like our sample holders, we have to provide a maximum care for the optics. So that's about the monochromators. Then next one is the dictators. The dictators which is used in case of in case of IR spectroscopy include the thermal dictators as well as the photodictators. This thermal dictators works on the principle that once this IR radiation falls on the dictator, it may produce some heat. So the heat is heat, or that can be converted into some electric signals, so that can be correlated with the amount of radiation. That is the basic principle behind the thermal dictators. Example for thermal dictators include the thermocouple, bolometer, and Golay cell. Okay, these are the major dictators which is used in IR spectroscopy. Okay, next one is the first IR dictator, that is thermocouple. A thermocouple is a simple, widely used device for detecting the IR radiation. It is constructed from two dissimilar metals, which is joined at one end to form a junction, which act as a sensing element. This junction is also called as hot junction, which is usually often blackened or coated to absorb maximum IR radiation effectively, while the other end of this metal are kept as a reference uh, temperature. That means it is called as cold junction. When the IR radiation strikes the junction, it heats the junction slightly and creating a temperature difference between the junction and the reference end. That means the temperature difference between the sensing junction and the reference junction will be generated. That means hot between the hot junction and the cold junction. This temperature difference generates a small voltage according to Seebeck effect, and the magnitude of this voltage is proportional to the amount of radiation which is falling on the detector. Since the voltage is very small, it is usually amplified before being recorded as an electric signal. This signal can be used to produce the IR spectrum that reflect the absorption characteristics of the sample. So we know that this the main advantage of this thermocouple, it is a very simple dictator. Working principle is very simple. Construction is also very simple. So this is the main advantage of this thermocouple as a dictator. But the response time, it may take some response time to dictate the to produce a proper signal. That is the main disadvantage of this thermocouple. Then the next component or next dictator which is commonly used is bolometer. A bolometer is also a typical thermal in IR dictator which measures the IR radiation based on the change in the electric resistance of the material when it is heated. It is typically constructed of thin electrically conductive elements, like some resistors are commonly we use. These elements are usually blackened or coated to increase the maximum absorption of IR radiation, then which is connected as a part of a Western bridge. Once we transfer the radiation, or once we allow the radiation, IR radiation to fall on this resistor, then the resistance of this particular resistor or blackened metal piece, that the resistance get changed, so which allowed a disturbance in the Western bridge, so we can see inflections in galvanometer. These inflections or the current which is passing through the galvanometer is directly proportional to the radiation which is falling on this resistance wire. So the basic principle we can conclude it as it is mainly working on the principle of Western bridge. So initially the bridge will be in a balanced way, but once the IR radiation falling on it, it may disturb the Western bridge by changing the resistance of the wire. So this change in resistance can be seen in as a inflection in galvanometer, which can be recorded as a function of intensity of radiation. That is the basic principle of bolometer. Then the next one is the Golay cell. Golay cell is actually a we can see that it is a simple metallic tube. This metallic tube is divided into two portions. The first portion, it is an empty tube where we can see gases like neon or some helium or something, some inert gases can be nitrogen, helium. This type of gases will be filled in this region. And we can see an IR window here, and the next portion will be separated by a diaphragm, a flexible diaphragm. Okay, then the next, the chamber, already we say that this chamber is divided into two parts. In the second part we can see a light source. This light will be passing through an optical system, so which will be reflecting from the mirror which is placed on the membrane. So once it is reflected, it will be measured by means of a sensing element, like light sensors are used. So in the initial phase we can see that there won't be any change in the shape of this diaphragm, but once the IR radiation passing through this IR window, once it is absorbed by these these gases get expanded, and this, because of this expansion, it will push this membrane. So that what happened is this diaphragm will get moved forward, so the pathway of this light may get changed, and the intensity of radiation falling on the light sensitive material or sensor which is placed on the second chamber may get changed. So we can say that based on the intensity of radiation, the gas may get expanded. The expansion will depends on the intensity of IR radiation. So the intensity of radiation which is falling on the second chamber, that also get changed. That is the basic principle behind a Golay cell. Then coming to the FT optical system, in case of Fourier transformation, we are not going to use any dispersive element like monochromators. Instead of that, we are going to use interferometers. That is the basic difference between the dispersive IR and the FTIR. Here we can see that the radiation from the light source is moving from is reflecting from a mirror which is passing through an interferometer. In this box we going to show the interferometer that it's working. So in this interferometer we can see a beam splitter which split the radiation into two components. So these radiations are going to move towards one moving mirror and a fixed mirror. Okay, so the mirrors will reflect back these radiations, and again this radiation is going to combine in this beam splitter. Then it is going to move forward towards the sample chamber and finally to detector. So what is the basic principle? What is the basic principle in Fourier transformation is, Here we are going to use the entire wavelength range instead of one by one. Selection may not be there in case of Fourier transformation. Here we are going to use the entire wavelength range. That is the main advantage of Fourier transformation. So here we are going to record the signal in time domain, not in wave number domain. Here we are going to record the spectrum in time domain. So particular 1 second, so in small time interval we are recording the spectrum. Then these spectrum will be converted to the wave numbers. Okay, that is called the Fourier transformation. So the main advantage of Fourier transformation is we will get the signals or the spectrum at the earliest. That means within a second we can generate the spectrum, and we can do the scanning many times. That means around 45 to 50 times we can do this scanning within a minute. So the resolution of spectrum will be very high. Okay, once again we can see what happened in this interferometer. Okay, we are focusing only on the interferometer because we already discussed about the other components. So once the radiation is passing through, is going to face the beam splitter, it is split the radiation into two. We already said that it is going to split the radiation into two. One portion it will be moving to moving mirror, and the next portion is going to face the stationary mirror. The stationary, the name, as the name indicates, the stationary phase is fixed one, so it won't move, but the moving mirror is slightly changing its position with the help of a motor. So what happened is, once the radiation is reflecting back, then the radiation, a new radiation with high amplitude will be formed if a constructive interference is happening. Or else what happened is, if the phases are different based on the position of moving mirror, sometimes the crest of a ray 1, that means that the radiation from the stationary mirror, we can call it as a ray 1. If it is ray 1 is the crest of a ray 1 is matching with the trough of ray 2, that is radiation from the moving mirror, then destructive interference will happen. So this is the output. So light wave 1, which is going to reflect, which can be represented as the light which is reflecting from the fixed mirror, and light wave 2 is can be represented as the light which is reflecting from the moving mirror. If both are in same phase, that means the crust and trough are in a matched position, then a new radiation A and B can be joined together and it will produce a high amplitude signals. But if they are in opposite phase, out of phase, then what is going to happen is, then destructive interference will be happening. So we can see that a pulsating effect can be generated with the help of this interferometer. That is the main advantage. Because of the position of this moving mirror, constructive and destructive interference is going to happen. Okay, then if you're comparing the dispersive IR and FTIR, we already said that dispersive IR means we have to disperse, or we have to select the wavelength one by one, then we have to measure the intensity in a detector. What happened is, we have if you're going to select the wavelength by one, then it may take more time. So that sample may get, if you are going to radiate a sample with higher radiation, it may heat the sample. So if the sample is a thermolabile material, it may destroy the sample, the nature of the sample, and also it may take a long time also. But in case of FTIR, the main advantage is the better resolution and the time factor. Okay, I think you may get the points. We discussed mainly about the components of a instrument, like the light sources, sample holders, dispersing elements, interferometer in case of FTIR, and the detectors. The major components we discussed, and we see the basic difference between the dispersive spectrophotometer and FTIR. Okay, I think uh, the topic is clear for you. Thank you. Thank you very much.